we're going to look at the central limit theorem. Again, this is a memorize what the meaning of the central limit theorem is. We have a distribution that is not normally distributed. Okay, this is going to be the definition. We sample from this distribution and summarize the results using a sum or an average. Now, if the sample size is large enough, then the sampling distribution of the sum or average will have a shape that is, again, approximately normally distributed, meaning we will pretend it is normally distributed in order to calculate probabilities. So this is the central limit theorem. We're sampling from a distribution that is not normally distributed. However, if the sample size is large enough, then the distribution, the sampling distribution of either the sum or averages will have a shape that is approximately normally distributed. Okay. Now, this situation is known as the, again, as the title suggests, central limit theorem. The process of approximating probability is very common in statistics, so this idea is one that permeates. How big does the sample size need to be? Because the population distribution we're sampling B of any shape, we just have general rules. Let's say the distribution is symmetric with no outliers. So if that is the case, let's say approximately, I'm going to keep it nice and simple, 10. So an approximately 10 sample size would probably do it. Maybe 9 would do it as well. But 10, I'm just kind of pushing the boundaries and go, let's call it 10 and call it good. What if it's a moderate skewness, far right or left? So again, I'm going to just say, look, n would be approximately 25. Obviously, greater than 25 would do it, but at the lower boundary, let's just say if you're at least 25, then you're fine. N being greater or equal to 10, approximately, okay? So that's sort of a general rule. What if it's like severe skewness, right or left? Again, I'm going to just throw a number out here. I say that 40 would do it. But if you were to pick up a book, you would see different numbers in these distributions. Just again, to understand that there's not one thing. You might get this question and they say, look, how about this? I've seen it where all of a sudden, this is the boundary, 30. 30 is good. What about here? I've seen it where, look, it's 45. So again, are not hard rules. These are just general rules. If you're asked this in a question, again, will be just use your common sense. If it's moderately skewed, all of a sudden you chose, and the choice is 12, then you realize I'm not reaching 25, nor I'm reaching 30. If it's severe, again, moderate skewness, and it's 15, again, not reaching these. If you're, symmetric, and n is 10, that's probably fine. If it's severely skewed and n is 55, of course, that's going to be fine. Use your common sense. Let's look at the situation right here. This is definitely right skewed. And we did this before, and the sample size was 5. And when we did this, the sampling distribution looked right skewed. So clearly 5 is not big enough. Now, is this severe or just moderate? Maybe you would think, this is something in between moderate and severe. I mean, this is not exact size. So I'm going to reset this, get rid of all these, and now my sampling distribution, but let's pick a different size. Let's just try for fun a 30. Let's see if 30 would do it. Now I'm going to draw a sample of 10,000. And I did. This is the last. Now these are sample sizes of 30. Notice like there's 30 numbers here. And you'll notice that the shape now of these raw data looks just like the population. And that's what I would expect. Now, this 30 is more likely to represent the distribution I'm sampling for, a little more than just 5. 5 has a lot more variability, but 30 has a lot less variability, meaning I'm really getting close to what this thing looks like. But when I look at the sampling distribution, hey, look at that. That is a very nice, approximately normal shape. Now, if you look closely, you might say, well, look, there's a tiny bit of skewness here. Right, and that's what, so when we say it's approximate, what we're trying to say is that it's probably good enough to do calculations. But what does that mean? It just means, again, that you're going to be close enough, and close enough depends on your application. Some things might be close enough, some may not be close enough. Depends on what you're doing with this information. Let me reset and I'm now going to go 35 and see what happened. I'm going to draw a sample. And again, notice I don't see that big of a difference between 30 and 35. So again, you notice these are just kind of approximations. So keep that in mind. What if it just decided, maybe this is severe skewness, I need a 40. Let's try 40. Reset. And it's a little better. But I mean, almost imperceptible. 45. Yeah, notice I think I just spotted a little more, got better. But obviously, if I went bigger than those things, this is just a lower boundary. So if I did 60, look at that. Now I'm starting to notice this little right skewness is almost gone. So this numbers are just a lower boundary. Notice when I did 60, how much more representative that is. Notice again, the mean of this one now, if I did it over and over again, the mean of these are going to be closer and closer to the actual mean. Example, if I did this one, let's see if I can change them. Oh, I have to come over here and change them. If I click over here, it will change to a different one. Yep, 134, 125. And notice again, the closer I am here, then more likely this number will match close to that. But of course, if I go to these unlikely averages, then of course, notice less representative. But the ones that are less representative, as you can see, are not that likely to happen. These numbers at the edge here, sure they can happen, but they're less likely to happen. For example, here with this one, I will have an average of 172. And this is clearly not that far away. But again, the chance of any of these happening where it's not that representative is not that good. Most likely your average will be somewhere here. And then you go, oh, 131, 137, not bad. 140, 137, not bad. 125, a little worse, but anyway, these numbers are more likely to happen. And that means that the average it produces is going to be closer to this one. So if the distribution you're sampling from, population distribution, also known as the parent population, that's another word sometimes you'll hear, is normally distributed. Let's say that the one I'm sampling from is normally distributed. Then the sampling distribution is what? Exactly normal. For any sample size, it really doesn't matter at that point. If you're starting with a normal distribution, regardless of sample size, the sampling distribution will be normal. But that means that the parent population has to be normal.